Okay, everyone, so that's 2 o'clock CET, so I propose we make a start this afternoon. So you are very welcome. Good afternoon to you all. I'd like to welcome you to this afternoon's webinar, which is organized by TG 1.3 of IABSE. TG 1.3 is focused on the calibration of partial safety factors for the assessment of existing bridges. The title of the webinar today is the Assessment of Existing Bridges with Practical Implementation and Case Studies. This webinar will be recorded as per previous webinars, such as the webinar of the 26th of May on the assessment of existing bridges, which I'm aware that many of you participated in. All of the recordings are available on the e-learning webpage, and I think Brindy is going to post into the chat the link to the webpage for you. At the end of the webinar today, we will have about 15 minutes for Q&A, and we will conduct this via the Q&A chat function in Zoom. We're delighted to announce that we have 287 registered attendees for the webinar today, and this is fantastic. And we look forward to your active participation in the webinar today. My name is Alan O'Connor. I am Professor of Structural Engineering at Trinity College in Dublin, and I have the pleasure to act as your moderator for this webinar. I'm delighted to introduce to you the 5 speakers who you can see on screen who we will have today. We have Andre Orsesi, Fabrizio Palmisano, Vasul Boros, Maria Kustar-Maric, and Dominik Skakandic. They are going to begin by reminding us of the context for the assessment of existing bridges, and then they will use the webinar to illustrate its implementation in 2 case studies in Germany and Croatia. I would now like to provide you with an introduction to the speakers in the order in which you will see them today. So Andre Orsesi is Deputy Director of the Technical Department of Bridge Engineering in CERIMA, which is the Centre for Studies on Risk, Environment, Mobility and Urban Planning in France. He's an expert in reliability of infrastructure, structural health monitoring, management, maintenance, optimization, and life cycle costs. He is also a member of several international scientific committees and is chair of IABSE TG 6.1 on the effects of climate change on infrastructures. Andre will be followed by Fabrizio Palmisano, who is a research assistant of structural engineering at the Politecnico di Torino in Italy. Fabrizio is also a director of the engineering and architecture consultancy company, PPV Consulting. He is active in many international technical and scientific working groups. He is a fellow of IABSE. For the European Union, he was a member of the project team relevant to the revision of Eurocode 2 and was leader of the project team which developed a new Eurocode on existing structures. Vasul Boros is a research engineer in the structural dynamics and assessment team at the Center for Low Emissions Transport of the Austrian Institute of Technology in Vienna, Austria. He has worked for more than a decade as a civil engineering consultant in Germany and has extensive experience in the reassessment, strengthening, and structural health monitoring of bridges. He is a member of IABSE TG 1.3 and the newly formed TG 1.10 and of the DIN Standards Committee on Design Loads for Bridges. Maria Kustar-Maric is an assistant professor at the Faculty of Civil Engineering at the University of Zagreb. Her main research areas are bridges and durability of structures, including the prediction of service life and non-destructive testing of structures, as well as the effects of climate change and blast loading on structures. And finally, but by no means least, we have Dominik Skakandic, who is a postdoc researcher at the Department of Structures at the Faculty of Civil Engineering at the University of Zagreb. Dominik's main research areas are the assessment of existing structures and bridges, probabilistic approaches to reliability analysis, value of information analysis, and the modeling of traffic loads. He is a member of the IABSE Young Engineers Committee and a special advisor to the Croatian Minister for Construction regarding post-earthquake reconstruction. Just to note that Dominik will not be sharing his camera with you all today as he's a little bit under the weather, but we're delighted he's still agreed to join us for the webinar. Now I would like to present you with some background and context on behalf of IABSE, the International Association for Bridge and Structural Engineering. So IABSE's mission, as you can hopefully see on the slide, is to exchange knowledge and advance the practice of structural engineering worldwide. And this is conducted in relation to all aspects of structural engineering, all types of structures and structural materials, and all aspects of the construction process. IABSE is a very large organization with over 3,200 members in 100 countries. And you may be aware of your national committee, and if you're not, we would encourage you to reach out to that national committee and become involved. The webinar that you're seeing today, as I indicated at the start, is available via the e-learning platform, as are all previously conducted webinars. Furthermore, IABSE conducts a number of very high-profile international conferences, such as the upcoming conference in New Delhi in 2023 and the Manchester Symposium in 2024. And I would point out to you that abstract submission for the Manchester Symposium is currently available. And I think Brindy is going to post a link into the chat where you can access that. In addition, ABSI publishes a number of high quality publications. No doubt you're aware of Structural Engineering International, the flagship journal published by IABSI, but there are also a number of structural engineering documents, case studies, and guidelines which are available, in addition to the very many conference proceedings, which are a wealth of information and a resource to be accessed by practicing engineers. As I said at the outset, IABSI has a large number of national groups and task groups, and we would encourage you to become involved with those. There are a number of technical commissions, 6 in total, and very many task groups, greater than 40 at this stage. And Andre is a chair of a task group. I'm a chair of a newly formed task group. We would encourage you to, via the website, to look at the task groups and to become engaged with them. Today's presentation is on behalf of Task Group 1.3. If you're interested in the work being conducted, we would encourage you to reach out to the task group. If you are a young engineer, oh, I'm not going to play the video. Sorry. If you are a young engineer, then there are a variety of resources available to you. You can have free access to the journal from 1991 to 2003. You can have reduced IABSI conference fees. There are a variety of other IABSI publications which are available to you. And probably most importantly, there is a chance to meet very many international experts who you can gain valuable insights and expertise from. IABSI is very active at a national level in the organization of workshops, meetings, conferences, seminars, and technical visits. And very many of these will be of interest to you. So we would encourage you to reach out to your national group and find out about the activities which are ongoing, become involved with your national group, and become involved with the work of IABSI. Finally, I would point you to the e-learning platform where, in addition to today's webinar and previous webinars, you can also find keynotes, you can find lectures and courses, you can find reports, and you can find a variety of toolboxes. So I hope you agree that there are a huge array of tools and resources at your disposal, and we would encourage you to become involved if you're not already involved with IABSI to capitalize on those resources which are available. So now I'm delighted to start the webinar and begin focusing on the assessment of existing bridges with practical implementation and case studies. I'm going to stop sharing my screen and I'm going to hand over to Andre Orsesi to give his presentation. So Andre, it's over to you.
Thank you, Alan. Good afternoon to everybody. I'm going to present you the context of this work. Is it okay? Do you see my screen?
Yes, Andre.
Yeah, perfect. So, so the aim, just to remind the aim of this task group, when we started a few years ago, the objective was to illustrate these different formats that exist related to the assessment of bridges and to illustrate these formats with case studies. So it is some kind of task group where we discuss the assumptions, we discuss the different formats for bridge assessment, and we try to illustrate in a practical way the different steps of this procedure. And we have the chance, so you can see here, it's a screenshot of the website that you can visit related to this task group 1.3. We have the chance to have several members from different countries all over the world. So we have a quite general view of what can be done when we talk about bridge assessment. And we have the point of view of academics and practitioners, which is an important part of the problem. So the background, we rely on a lot of studies previously conducted these last years. There are a lot of scientific committees, also standards working on this topic, and we try to merge the information available from these different groups. In particular, the JCSS, everything related to Eurocodes, the ISO standards, the FIB model code 2010 and now 2020, and some documents, several documents related with the assessment formats for existing structures. So there are three main formats that we can develop, and today we are going to talk about the two first ones that you see here. The first one is the partial factor format, and using partial factors, and the second one is reliability-based format. Then if you include the consequences, you can reach the risk-informed format. So just a few words about the reliability-based format to mention that in this format, then we consider the a probabilistic level for the different variables, and we try to look at the to research the what we call the design point in the standardized space that you see on the right. And then when we find this point, then we come back to the physical space of the variables to identify this design point. And then it is possible to move to the partial factor format. So in fact, whereas it is a resistance variable on the left or an action variable on the right, then we calculate this partial factor as a ratio of a characteristic value and the design point value for this particular variable. And this implies to have information and the variability, like the coefficient of variation and what we call reliability index called beta. So this was some kind of basic problem, but we can generalize to different types of variables. I showed some results for normal distributions, but there are several other distributions like log normal or Gumbel distributions that we manage in this type of assessment problems. And then we come to the formats that are generally used when assessing structures, relying on the partial factors. So it can be fixed partial factors, considering a cluster of cases, and then we fix the partial factors to be used in the determination of the assessment effects and the so EA and the resistance variables, or we can move to a format when we try to adjust the partial factors if we have some additional information for a particular case study. So today we are going to illustrate that with the case studies. And what we will also illustrate, so relying on the recent documents from the Eurocodes, FIB, as you can see on the top of the right, when we try to adjust the partial factors, so for individual case studies, then we can have different ways to do that. We can have some what we call single partial factor, when in fact one factor for a particular variable will cover the different types of uncertainties about, if we talk about material variables, the material property, the geometrical variables, and the resistance uncertainties, so on the left. Or we can separate the partial factors if we consider first the material property, then the uncertainty of the resistance model, and the uncertainty of the geometrical variable. So we will illustrate these two different ways of considering the uncertainties when we try to adjust the partial factors. And then now I will shortly introduce the two case studies that we will present today. So the first one is a reinforced concrete slab bridge built in Germany in the 1970s. And you see here a view of this bridge. And first, we will apply a semi-probabilistic format with fixed partial factors. Then we will show if we adjust the partial factors relying on the single partial factors, as well as separate partial factors. And what will be presented will be the influence of the number of in situ concrete tests when we try to get information from in situ. And then finally, we move to the higher level of assessment, which is the full probabilistic analysis applied on this case study relying on what we call a first-order reliability method. And then we will present a second case study, which is a continuously reinforced concrete slab bridge built in 1961 in Croatia. And we will have similar three-step approach, starting first with the fixed partial factors, then adjusting the partial factors and moving to a full probabilistic analysis. And we will illustrate the results both using the LM1 action model from Eurocode or site-specific traffic load models. So we will illustrate these differences with this case study. And finally, the results that are presented today will be available soon in a SEI journal paper from the IAPSE journal. And this paper is almost in the way of being published, so you will have more information soon available also with this paper. And with that, I finished this short introduction, and I'll give you the end back for the next presentation.
Thank you. Thank you, Andrea. Thanks, Alan, for the nice introduction. And good afternoon, ladies and gentlemen. Well, I will talk about the first example, the case study number 1, and I will talk about a brief introduction on the case and the material partial factors. Then the case will be completed by Vasul Boros immediately after me. The background. This is a very simple bridge. For this example, we drew inspiration from a real case study, but we made some changes to the original one in order to better highlight some issues relevant to probabilistic and semi-probabilistic approaches. This bridge is a reinforced concrete bridge built in Germany about 50 years ago. The analysis will be limited to the deck, which is a 75 centimeter deck with a net span of about 9 meters. The assessment of concrete strength has been done directly on the deck by using the approach given in EN 13791 by drilling 8 cores and calculated the in situ characteristic value of concrete by using the approach given in section 8. I don't have so much time to go into detail, but all the data are given in this section of this code. The reinforcement of the slab is composed of 20 millimeter bar diameter with a spacing of about 12 centimeter. And the yield strength has been assessed by taking sample and test laboratory, but by using, and the general characteristic value has been obtained by using a log normal distribution. Before starting to talk about the material partial factor, we have to determine the FCK, the characteristic value of concrete strength, from in situ test, because what we have obtained from EN 13791 is the value of FCK in situ, because we have to obtain from test and course driven by the concrete strength. However, all the formulation given in the code, for example, in the Eurocode, are make reference to the FCK. So this is it is necessary to pass from FCK in situ to FCK. I will show you the approach that we have used also in the case study that will be given in the forthcoming Annex I of the second generation Eurocode. This approach is based to the assumption that the in situ strength is the product of 3 parameters: the resistance of on cube specimen of concrete FC, a parameter eta core actual that is a reduction factor which accounts for the damage sustained during core extraction, and an in situ factor eta AS which takes account of the effect of curing, effect of consolidation of fresh concrete, and anisotropy. These variables are assumed to be random variables, log normally distributed, and stochastically independent. By assuming the parameters that will be given in the new Annex A of the second generation Eurocode and others taken from a recent study by Moccia Italia 2020, it is possible to obtain a factor that is applicable to FCK in situ to obtain FCK. And this factor in this case is more or less equal to 0.85. However, this approach is rigorous for cores extracted from the region governing for the verification. We have to, and this is the case that is highlighted in the section C of this table taken from Annex I of second generation Eurocode 2. However, we should take into account that in some cases, the cores are not taken directly from the region governing for the verification. So in that cases, we have to consider also the difference in resistance from the top and the bottom of the member of the element. We have the Eurocode has used a recent study by Boccia Italia, and by using this study and by using the same approaches that I have already showed, two different coefficients are derived for these cases. All the details will be included in the background document to the Eurocode 2. However, in our case study, the cores have been driven directly into the deck. So the coefficient to be taken is 0.85 and FCK is equal to 20 megapascal. Let's move to the partial factor. First, we have to talk about the fixed partial factors. And the current Eurocode has not a difference between existing structure and new structure. So we have referred to the partial factor given for new structure for a reference period of 50 years. These are equal, as we know, to 1.5 for concrete compressive strength and 1.15 for reinforced steel. In general, it is possible to use directly this fixed partial factor if first the coefficient of variation of material are very similar to those assumed to calculate the partial factor for new structure, and this is the case. Second, if the beta factor, the target reliability index, is the same as that given for new structure. In our case, we have considered that talking about an existing structure, we have reduced, as shown in the previous webinar, the target reliability index from beta equal to 3.8 to beta equal to 3.3. So the necessity to adjust the partial factor arises. So let's move to the adjusted partial factors. As Andrea has already said, we have used two different approaches. The first that we have called single partial factor approach, and the second called approach with separate partial factor. For the first approach, the single partial factor approach will make reference to the forthcoming Eurocode 2 and to FIB Model Code 2020 that will include this approach. In this, the basic assumption is that the general variable of the concrete strength, RC, is a product of the FC, the compressive strength of concrete determined from sample taken during casting, the in situ factor at IS, and the geometrical and model uncertainties. All these variables are assumed to be statistically independent and log normally distributed. So by making this assumption, is it possible to calculate the gamma factor for concrete as the ratio between FCK and the design or assessment value of RC. And the expression is an exponential function, which is a function of the sensitivity function that for dominant variable we can assume equal to 0.8 for resistance, the beta target value, target index that, as I've said, in this case will be equal to 3.3, the coefficient of variation of RC, that is a function of all four parameters, and the bias factor of RC, that is a function of all parameters. However, this formulation is correct from the structure when we assess the FC, the FCK. For existing structure, we assess the in situ value. So a modification is needed, and this modification will be included also in the second generation Eurocode 2, and will be a function of the sensitivity factor, the beta factor, and also of the number of test results, because we have to consider that if the number of test results is low, lower than 30, the function, the random function to be assumed is more similar to a TD student than to a log normal function. It is worth highlighting what happens when dealing with the number of test results and the increase of coefficient variation of concrete strength. In this graph, it's quite evident that if we have a coefficient of variation of a seed concrete strength greater than about 0.15, the relevant material concrete partial factor is greater than that we assume equal to 1.5 for new structure. So we are not on the safe side anymore. However, we can reduce, by using the formulation that I've just shown, this scatter by increasing the number of specimens, for example, from 8, that is the minimum requested by EN 13791, to 10, 16, etc. It is worth noting also the great influence that has the target reliability index on this evaluation. In fact, for example, if we pass from beta 3.8, that is more valid, let's say, for 50 years reference period for a new structure, to beta 3.3, so for an existing structure, there is a strong reduction in the material partial factor. And as we can see, in many cases, also for coefficient of variation of about 0.2, the material partial factor for concrete is lower than the one that we assume for new structures. The same expression is included in the forthcoming Eurocode 2 also for steel reinforcement. The only difference is that there is not difference between the in situ value and the value for a new structure of in strength, but the formulation is the same with similar assumption. It is worth mentioning that in Annex I of the forthcoming partial factor, the adjustment will be recommended and not only permitted if the coefficient of variation for either concrete strength or the steel reinforcement is greater than some limit value given by this annex and that are a function of the number of test results. Because in this case, we are not on the safe side anymore, as I've shown from the previous graph. So, by applying this approach to the case study, assuming a beta factor of 3.3, a sensitivity factor of 0.8, and all the values that are explained here and are better explained in the forthcoming journal paper, we obtain that gamma C is equal to 1.36 and gamma S is equal to 1.11. So both of them are lower than the value obtained for fixed partial factor for new structure, and the difference is not relevant to the coefficient of variation of material property, but mainly to the reduction that we have assumed for the beta factor. Let's move to the approach with separate partial factors. This approach will not be included in the second generation Eurocode 2, and in the Model Code 2020. So we have made reference to the FIB Bulletin 8. In this approach, the gamma factor for material is the product of 3 different partial factors. One takes account of the uncertainty relevant to the materials, and the other to the uncertainty relevant to the model, resistance model, and geometrical uncertainty. The peculiarity of this approach is that we can assume a sensitivity factor, for example, equal to 0.8 for a dominant variable, for example, the resistance, the material resistance, and while at the same time we can assume different sensitivity factor for the other variable. For example, we can assume for non-dominant value and new values that, according to Koning-Hofser 1982, can be assumed as equal as the 40% of the one assumed for dominant variables. So by making the same assumption of the previous approach and by make some calculation, we can obtain the specific formula to be used for in the approach with separate partial factor. Again, all the detail will be included in the journal paper. And for the case study, we will obtain that the concrete gamma factor is equal to 1.34, while the steel gamma factor is equal to 0.99. In both cases, again, they are lower than the one for new structure. And again, the main difference is relevant to the assumption of a lower beta factor. So let's conclude by making a comparison of the 3 different approaches. By using the adjusted partial factor method, in all cases, since we have reduced the beta factor, and we have a coefficient of variation of materials very similar for the one assumed for the structure, we have a reduction of the partial factor from fixed partial factor to both method of the adjusted partial factor. However, we can see a very important difference in the two approach of adjusted partial factor with reference only to steel reinforcement, because for the case of concrete compressive strength, the results are very similar. For steel reinforcement, there is a reduction of about of more than 10%. This reduction is mainly due to the possibility in the approach with separate partial factor to use different sensitivity factor and to use only the greater value of the sensitivity factor for a dominant variable. This, in these cases, when there are variable with very similar coefficient of variation, with this approach, we don't overestimate the material partial factor as it happens in our case study. And with this, I've completed my example, my part, and I will pass the baton to Vasul. Thanks a lot for your attention.
Yes, thank you very much. So I will continue now with the action part for case study 1, and also introduce you to some of the results that we obtained from these approaches. So obviously, this part of the presentation will be very similar from the structure than the previous one. So first, I'm going to talk a bit about the partial factor formats, first with the single partial factor approach. So here, just like with the resistances, we distinguish between concrete and reinforcement steel. Here we need to distinguish between the permanent loads and the live loads or traffic loads in case of the bridge. And the permanent load is basically consisting of the self-weight itself, and just like with the resistances, also from the model uncertainty. And therefore, if we use the single partial factor approach, also the variation coefficient consists of these two factors. So it's basically the square sum of the two. Also for actions, we need to consider the sensitivity factors, which are here 0.7 or minus 0.7, just like given in the Eurocodes. And of course, also on the action side, we reduce the reliability index for existing structures to 3.3 for a 1-year reference period. What is, of course, different here is the coefficients of variation. So we have a coefficient of variation for the model uncertainty and for the self-weight of in situ concrete, which are both taken based on the FIB Bulletin 80. So if we calculate with these values the adjusted partial safety factor, then we obtain a partial safety factor of 1.2, which also here is significantly lower than the 1.35 that we would use for a new structure. So if we move on to the single partial factor approach for the traffic load, then we have to assume a Gumbel distribution if we go according to the FIB Bulletin 80, which makes the calculation a bit more complicated. However, the principle is the same. It basically only depends, once again, on the sensitivity factors and the reliability index, which is significantly reduced. Once again, the coefficients of variation, both for the model uncertainty and also for the traffic load, are of importance. And one additional thing for the traffic load, which is important, is to the definition, basically, of the characteristic value of the traffic load, which in the Eurocodes is given as the load with the 1,000-year return period. And then if we calculate the partial safety factor for Gumbel distribution with these parameters, then once again, we get a significant reduction of 1.17 instead of the 1.35, which you would have for traffic loads. So this was the single partial factor approach, and now we will also address for the actions the approach with separate partial factors, as shown in the Fib bulletin. So here, as we've seen before, we can also divide up the permanent load into the product of a safety factor for the self-weight itself and another one for the model uncertainty. The self-weight itself would be, in this case, could be calculated to a partial safety factor of around 1.09, and the partial safety factor for the model uncertainty also here can be reduced with the factor of 0.4, as Fabrizio has explained, for the non-dominant part, which is in this case the model uncertainty. And once again, if we multiply these two partial safety factors, we get the overall safety factor of 1.03, which is significantly lower than the 1.35 you would normally have. So if we look at the separate partial factor approach for the traffic loads, we still assume, of course, the Gumbel distribution. And also here, we divide it up into the partial factor for the live load itself and the model uncertainties. For the live load itself, with the Gumbel distribution, we can obtain a partial safety factor of around 1.07. And for the partial factor for the load uncertainty, once again, with the reduction of 0.4 for the non-dominant basic variable, we get also around 0.7. So in total, the partial safety factor for the live load would be 1.14. So lower once again, as we would normally use with 1.35. So in the case of the actions, we didn't do any real measurements like we did with the resistances, but what we could do is something similar, which is to do some traffic simulations, which were actually considering the geometry and the load of the bridge. So here we assumed 5 different types of lorries, which we took according to the fatigue load model 4 of the Eurocodes, at least concerning their geometry. So I mean, like the axles and the axle geometry. However, when it came to the weight distributions, since this was a bridge in Germany, we used some measurements which were, first of all, more recent than the Auxerre traffic that was considered in the Eurocodes back then. And also it was more close to our bridge since it was taken from Germany. So this is all with the exception of Lorry 2, where no data was available. So there we had to refer to the Auxerre traffic. So anyhow, these were the weight distributions for the vehicles that we considered and the geometry. And another issue which we asked ourselves is which type of dynamic amplification factor needs to be considered. So after some discussion in the group, we decided on an approach where the dynamic increment is basically decreasing with a higher weight of the vehicle, as you can see here. So basically, it is normally distributed with a mean and standard deviation of 41.5 divided by the vehicle weight in kilonewtons. So these were basically the parameters for the simulation. And we simulated 2 years with 280 work days and different and distinguish different traffic categories, which are at least typically defined in the Eurocodes. So for the motorways, so one with 2 million vehicles per slow lane a year, and one with 500,000 vehicles. And we also considered the probability of a second vehicle in an adjacent lane. And after that, the results were approximated by a Gumbel distribution, as it is given, for example, in the Fib bulletin 80, and also in a more, let's say, generalized approach with the generalized extreme value distribution. And if you provide the characteristic values which we would get from these approaches, you can see that while there is a difference, the difference is not very significant. And what is even more important, the characteristic values obtained are about half of that what you would get if you would use the actual load model 1 from Eurocode 1. So there is a tremendous potential in reducing the traffic loads on the bridge if you consider the real bridge traffic and geometry. This is actually in line with several investigations which have shown that for short span bridges, the Eurocode model is rather conservative. And for this bridge in particular, we could see that this is really very much the case. So if you are more interested in these traffic simulations, there has also been an IAPSE paper in the conference in 2021 in Ghent, and there Belgium, and there we discussed a bit more in detail these calculations. So if we want to compare the results, I also included here the departure safety factors previously shown by Fabrizio and the new ones that I shown for the actions. Then we can see that for a new structure, we would get with the departure safety factors that are to be used for, according to Eurocodes, we would get a ratio between actions and resistances of 132%. So the unity check could not be fulfilled. However, already if we move with the adjusted departure factors of a single factor approach, we can reduce departure safety factors to a level where the check provides 111%. So still not fulfilled, but well, at a lower level. While when we are using the adjusted departure factors with separate factors, then we would even be able to fulfill the checks. And these were all, however, still with the Gamba distribution based on the fibulatine. And if we consider the simulations that I've just shown, then you could further decrease, of course, the characteristic loads the characteristic loads for the actions, which would further reduce these percentages by about 20%. So you would be able to prove that the structure is actually safe after all. As we said, there has also been a further, more, let's say, sophisticated approach to check the safety of the structure, a full probabilistic analysis using the first order reliability method form. And this basically, used the formula, the calculations of the bending moment resistance and the acting bending moment based on the formulas and notations shown in the present picture. And what is, of course, even more important for such a probabilistic analysis is the basic variables that were assumed. So on the resistance side, it was the concrete compressive strength and the steel yield strength, as well as the slab thickness, which also had some effect on the self-weight. And of course, the model uncertainties for resistances. And on the action side, it was the concrete density, the bridge span, so basically a geometric parameter, and the density of the cover, so the asphalt layer, as well as its thickness. And of course, also here, the model uncertainty, and as well, the moments due to traffic. But here we distinguished the case 1, which was basically the Gamba distribution based on fibulatine 80, and case 2, where we also use the Gamba distribution, but from the simulation, so with a significant lower level, and also a lower coefficient of variation. So if you compare the results, then for case 1, we got a reliability index beta of around 3.33, which aligns well with the calculations with departure safety factors, since we were approximately around the 100%, depending on which way you look, 90 to 110, with a reliability index of 3.3. And if you look at case 2 with the simulations, then the reliability index increases significantly. So there a much higher reliability could be proven. And maybe what is also interesting to note is the sensitivity factors of the different basic variables. So you can see that with a decreased characteristic value in the traffic loads, the sensitivity of the moment due to traffic decreases significantly. And what I think is also interesting to note that the model uncertainties of both actions and resistances have a very high influence on the results. So this was the summary for case study 1. And now I hand over to Maria for case study 2.
Good afternoon, everyone. Do you see my presentation? Okay. The Croatian case study is prepared by Ana Mandic-Ivankovic, Dominik Skokandic, and me, and will be presented by Dominik and me. I will start with introduction, bridge description, and application of design value method proposed in FIB Bulletin 80. Then Dominik will continue on VIM analysis, multi-level assessment, and conclusion. So let's start. The second case study is 3-span girder reinforced concrete bridge on state road in Croatia. Assessment is provided in 3 steps. In the first step, the linear analysis is conducted using a semi-probabilistic partial factor format and the values for structural design of new bridges along with traffic load model 1 according to Eurocode. In the second step, again, semi-probabilistic approach is used, but partial factors are adjusted using the design value method based on FIB Bulletin 80 for both the reduced traffic load model 1 and the VIM model developed for this case study. Finally, in the third step, the assessment is performed using a fully probabilistic reliability analysis, relying on the first-order reliability method. Croatian case study is Posedarje Bridge. The bridge is built in 1961. Bridge spans are 9, 15, and 9 meters, while bridge length is 33 meters. The slab is supported by concrete hinges on piers and the first abutment, while on the second abutment, movable bearing is placed. Bridge slab is 0.6 meter deep and 8.5 meter wide. Bridge is designed according to codes from 1949. And designed concrete strength corresponds to C3037 according to the Eurocodes, while reinforcing steel quality is S220B. Original design plans along with built-in reinforcement are available, including all structural elements. Here are shown for concrete slab. And concrete slab is reinforced with Fe20 plain bar reinforcement. Results of visual inspection show that the bridge is in good condition. In the second step of bridge assessment, partial safety factors prescribed in Eurocode for new structures are reduced using design value method. And according to draft FIB Model Code 2020, an annual target reliability index of beta 3.3 is considered for the medium consequences class. The material factors for concrete and reinforcement are determined as shown, where gamma RD1 and gamma RD2 are recommended values for model and geometry uncertainties in FIB Bulletin 80, assuming a log normal distribution of material property. The material partial factor gamma m is obtained from this equation. with following coefficients of variation: 0.15 for concrete and 0.05 for steel. Alpha R is 0.7 and beta is 3.3. Note that there is no in situ measurements available for this bridge. And it is also worth to mention that for some other input data, such as alpha, coefficients of variation, and beta, FIB Bulletin 80 provides graphical determination of gamma M for steel and concrete, which is a more user-friendly option. Partial factor for permanent load, gamma G, is calculated using an approach similar for material factors, assuming normal distribution and following coefficient of variation 0.1, alpha E is minus 0.8, and same beta. The value of gamma EDG used for this case study is based on the recommendation of FIB test group 3.1 and is equal to 1.07. Again, for some other input data, alpha C and coefficient of variation and beta, FIB Bulletin 80 provides graphical determination of gamma G, but also for gamma Q. And finally, the partial factor for variable load effects, in this case, in case of bridges traffic load, is calculated as product similar to the one for permanent action. But the reliability base factor gamma Q differs for load model 1 and VIM model. Namely, coefficient of variation for VIM model is much lower than coefficient of variation for load model 1 from Eurocode. More about VIM model and further assessment will be now presented by Dominic. So this is all from me. Dominic, please continue.
Yeah, thanks. Thanks, Maria. Could you please shut down your screen so I can share mine? Yeah.
Sorry.
Hello, everyone.
Okay.
We will have presentation in a second. Before I start, I'm a bit. I have a cold, so I turned off my video because I feel bad, but I look even worse. So don't hold that against me. As Maria said, I will now continue more regarding the traffic load modeling for case study bridge in Croatia, and then I will provide you the results for all three steps or levels of that multi-level analysis. But first, some basic introduction, but I guess that you are all well acquainted with the traffic load models in for new bridges. Precisely, these ones are from Eurocodes. Those are based on the weight and motion data, but only limited amounts, so they're very conservative, which is really good for new bridges, but it's not suitable for application in the assessment of existing ones. This picture here shows two different types of traffic situations. The one on the right is free flow traffic, and the one on the on the left is a traffic jam situation. The one on the left has more effect regarding the static load, and the one on the right regarding the static load amplified by dynamic factor. And that dynamic factor is an important, very important parameter when assessing the existing bridges. Just a second. As you can see here, this is this is a diagram from Eurocode load models. So dynamic factor is the amplification we use to increase the static load weight of vehicles. And you can see for smaller bridges, this is 100 meters, this is 0. So for smaller bridges, for example, bending in one lane, the amplification can be even 50%. The irony here is that when using weight in motion or bridge weight in motion technologies like we used here on this case study bridge, you can directly measure the dynamic factor for each vehicle, and dynamic factor is decreasing with increased weight of the vehicle. So the dynamic factor for trucks and lorries, which are the ones that we are looking, because the regular personal cars do not have any effect on bridge. Dynamic factor for those are around 1.05, 1.06, which is significant decrease when compared to the ones that Eurocode load models have already built in. So for the case study bridge, we collect the traffic data and then calculated the load effect for each vehicle. That's a really simple procedure using influence lines for movable load. And key factor here is extrapolation of that data, because there are several extrapolation methods, but that's not the topic for this webinar. So I will not go in details on that. And then the obtaining of target values. In our case, for case study bridge, our target values is bending in the middle of the central span and negative moment on both piers. Also, just a short introduction, although Andrea already said that in the first presentation, semi-probabilistic method, the one where the uncertainties are covered with partial factors, are used for this multi-level analysis, but also for step 3, full probabilistic method is used in order to showcase the benefits of full probabilistic approach, and FORM method, first order reliability method, is used in particular for this case study bridge. So first of all, we needed to define the limit state equation, which is, although it looks complicated, it's rather simple. We have a bending moment resistance of the bridge and the bending moment which is acting on the bridge. That one is just a superposition of bending moment of self-weight, additional dead load, and traffic load, each with its own uncertainties. And here we have a bending moment resistance, which is calculated based on the reinforcement area, steel yield strength, effective depth, and geometric measurements of our bridge. This is the table which presents all of these variables, distributions which are used for full probabilistic approach in step 3, mean value and coefficient of variation. For first 2 steps, we use the target values as prescribed in the Eurocodes, and the partial factors as you will see now. So in the first step, we use partial factors for new bridges. So for material 1.5, 1.15, and for both prevalent and traffic load 1.35. These are the values for resistance, value for load effect. Here, dynamic factor is not taken into account, or it is taken as 1, because Eurocode traffic load models already have built-in dynamic factor. You can see that the result is presented as a ratio similar as in case study 1 between the load effect and the resistance, and as in first step it's 135%, which means that the bridge cannot be assessed as safe. It's really simple. If the result, if this ratio is over 100%, you cannot assess the bridge as safe. Therefore, we proceeded to the second step, in which we used the reduced partial factors obtained with the design value method, as Maria showed you in the first part of the presentation. You can see them here. So for concrete, it's 1.34, steel 1.11, permanent load 1.31, and traffic load 1.16. So both the resistance and the traffic load effect, resistance has increased and traffic load effect has decreased, and therefore the ratio is a bit more. It's a bit better, but it's still over 100%, which means that the bridge is still not assessed as safe, and therefore we proceeded to the third level, where we substituted the Eurocode traffic load effect with weight in motion calculated site-specific load model and corresponding dynamic amplification factor. And in first, we just we left the same partial factors, and we repeated the same analysis as in the step before, just with the reduced traffic load effect, and we obtained even better ratio, but it's still a little around 5% over the threshold, so the bridge is still not assessed as safe. And in the end, we conducted a full probabilistic analysis based on this limit state equation and the corresponding values. And for the third step, fortunately, it's not in the presentation, I forgot, but in the third step, we obtained a reliability index of around 4.2, which means that the bridge can be assessed as safe in the final step of the assessment. So so to conclude, we have a nice comparison of three levels. Here, partial factors for new bridges, then adjusted partial factors, but in first two levels, traffic load models are used for new bridges, and in the third level, traffic load model is based on the measurements, so site-specific load model. And using semi-probabilistic approach, we can see the decrease in the ratio. In the end, it's still over 100%, but when we used full probabilistic approach, the corresponding reliability index was over 4, so which means that we can assess the bridge as safe for the chosen reference period. So these comparisons, I think it represents really clearly the effect of using reduced partial factors. That's the first one. Then the benefits of using site-specific load models when available, when the data is available. And in the end, the benefits of using full probabilistic approach, because using the semi one, we are very near. The results is very near to bridge to be assessed as safe. But when we use the first order reliability method, full probabilistic approach, the bridge was assessed as safe. And with that, I would like to conclude, I think, all today's presentations. And if I'm not mistaken, now we have some time for Q&A session. So thank you for your attention.
Thank you very much, Dominic, and thank you for soldiering through when you weren't feeling great. So that was super. I'd like to thank all our speakers today for a very complimentary and comprehensive set of presentations. We have, as indicated, a Q&A box in the Zoom platform, which we'd like you to use. I have a number of questions there that I'll begin to discuss now, but please feel free to type any other questions which you may have. We have some time left now, so let's capitalize on these experts to ask them the questions which are of interest to you. So the first question refers to the reliability, the calculation of the reliability index beta. So I think that was discussed by Vasul in his presentation, so I'll move on from that. The next question is about the bias factors. And how do we arrive at the particular distributions, for example, log normal distributions in the context of some of the parameters. So perhaps Vasul, you kind of discussed the distributions first. Maybe you'd like to discuss how you arrived at particular forms for the distributions used.
Okay, yeah, well, I mean, it was a matter of discussion in the group. I mean, mostly we refer to Fibulletin 80. Yeah, in some cases we used also some other sources, but basically it was mostly based on literature.
Super, thank you for that. And just to complement that answer, if you refer back to the webinar of the 26th of May, we also discussed some aspects of the choice of particular distributions for modeling loads and resistances. So you can access that webinar via the e-learning platform. So the next question comes from João Andre. Hi, João, nice to have you on board today. And maybe I'll put this to Fabrizio. I won't read out the full question, but it refers to aspects related to hidden safety, updating of variables, sensitivity factors, and being very careful in how we make choices in performing our analysis and not, as João says, cherry pick in the analysis we perform. So I think Fabrizio, I'll pass this one to you if that's all right to deal with.
Yes, thanks, Alan. Thanks, João, for the interesting comment. I agree with you. We have to pay a lot of attention when dealing with the adjusted partial factor, because there is hidden safety, model uncertainty that in many cases we have some difficulties to evaluate in general for new structure and in particular for existing structure. This is why, for example, in the second generation of the Eurocodes, there won't be a general freedom for the practitioner to adjust the partial factors, but they will be given in the relevant Eurocode. For example, in the Eurocode 2, as we have shown, there will be a procedure that can be applied, and in this procedure, some values are suggested. For example, model uncertainties, geometrical uncertainties. There are also some formulation to differentiate or to better evaluate, for example, the geometrical uncertainties. While in other cases, they will be NDPs, so national determined parameters. So there will be some countries which can give some procedure or not. We have discussed a lot within the SC10, for example, and in a small group of SC10 in the TC250. And there are some issues relevant, for example, to the adjust of partial factor relevant to action. Let's think about wind, etc. And to be honest, I don't think that there will be a specific NDP to adjust this partial factor. But for the time being, as I said, we have for concrete, and maybe they could be given for some permanent action, etc., or traffic load.
Super, thank you for that, Fabrizio. Very comprehensive answer. I think that also deals with the aspects related or raised in the next query about validation of estimation. So I'm happy with that. Andre, a chance for you to promote the work of the task group. Is there a way for us to access the papers of the researchers presented? So I know you had indicated, Andre, the upcoming publication in SEI, and Vasul in his presentation spoke about the presentation again. So I'll hand over to you, Andre, if you want to promote some of the work which is done and where that can be accessed.
Yeah, all this work is going to be published very soon. We are just at the stage of checking the proofs. So really, I think within the next few weeks, the community will have access to the results applied, and you will find these two case studies with the first one and the second one, and the main results, the main developments with this multi-assessment formats and the comparison of the assumption behind. There were already some presentations previously at some conferences like the one at the conference in Ghent, as Vasul you mentioned. For example, the development for the load side. So the people might check in this previous publication, and also if they have some question, they can contact us directly to have more information about where we are today.
Thank you very much, Andre. And Brynda has also posted in the chat a link to where papers are available. So please consult that. So our next question comes from our friend Mirek Sikora, who, if any of you didn't see, Mirek gave an excellent presentation on the 26th of May, and you can refer to that via the e-learning page. So Mirek has a question for Fabrizio. So when information about concrete compressive strength is based on non-destructive tests calibrated by a few cores, say 3, for a particular structure, how should the value of partial factor gamma C be specified for this structure?
Thanks, Mirek, for the question. If you apply the procedure in EN 13791, you can't use only 3 cores to assess concrete strength. The minimum for a type of concrete is 8 cores. And this is why the table shows starting from 8. And however, you can use non-destructive tests validated on the core result to have more test results. So at the end, you can use all the test results you have, destructive and non-destructive, to reduce, for example, the gamma factor by adjusting it.
Thank you, Fabrizio. So the next question is a general question about will a recording of this webinar be available later on? So yes, as we've indicated, that will be made available, as with all previous webinars. So the next question is from our friend Bruno Godard, who has another question for Fabrizio. I have some trouble with the concept of attaining a partial safety coefficient below 1 for the steel material. Something wrong with the concept?
Well, thanks, Bruno, for the question. In general, the partial factor can be lower than 1 because this is a simple ratio between the characteristic value and the design or assessment value. So it depends on the relevant probability associated. But in practice, we won't take a partial factor lower than 1. In fact, also all the partial factor given are greater than 1. So this is just an example, but in that case, we will take is equal to 1.
Great, thank you, Fabrizio. Okay, now a question from Serge Montens. So Vasul, this is for you. For example 1, the separate partial factors method was less conservative than the single partial factor method. Is it a general result?
Well, I mean, I'm not sure it's general, but the reason behind it is, I believe, as Fabrizio explained, that in the case of the separate partial factors, you can reduce the sensitivity factor for the non-dominant variable, and therefore they tend to be, less conservative. So I don't know, Fabrizio, if you want to add on this, but I believe this is the reason.
Yes, I agree with you, Vasul. It was in that case because we had similar value of the coefficient of variation for the parameters relevant to steel reinforcement. This is why. But in general, if it is not the case, the result will be very, very similar.
Super, thank you. So the next question is from Dan Ialomitino, and a chance for you, Fabrizio, to publicize the excellent work of the task group on assessment of existing structures. So the question is, when are the second generation ENs for assessment issued? It was mentioned 2023, and what is the date for being adopted? All
the Eurocodes will be made available by 2026. And this should be adopted by 2028. That is the date when all the first generation Eurocodes and the codes in contrast with the second generation will be have to be withdrawn.
Great, thank you, Fabrizio. Okay, Andre, one for you on the theoretical basis. So when you say full probabilistic approach, Do you compute the reliability index as the inverse cumulative normal distribution of the probability of failure, even if you used a non-normal distribution function?
Yeah, in fact, we rely on the form, so first of order reliability method, in which we convert the different types of variables using probability transformations into the standardized space, and where we have this iterative research for the design point, and then we come back iteratively from the standardized to the physical space for the variables. So we can consider not only normal variables, but different types of variables, like we introduced log normal and Gumbel and so on. So we considered different types of variables in the two case studies.
Thank you, Andre. So the next question is from our friend Lennart Elfgren. Lennart, lovely to have you on the call today. And the question is, are you planning any tests to calibrate the methods with tests to failure of bridges which are going to be decomposed? Fabrizio, you look like you want to take that one.
It is desirable to do that, but we're not planning to do this, at least in this task group.
Great, thank you. And Lennart, I think that's a very good advertisement for the fantastic work which you've been doing for a number of years, looking at structures which were being taken out of service and validation of some of the computational models which we have. So thank you for your question. Okay, the next is from an anonymous attendee. Excellent presentation. Are assessments using other materials such as cast iron structures will be considered in the future? We have assets which are 140 years old. Who would like to take that?
If I may, I could say what will be included in the Eurocode. In the project team, that Alan was also a member of the project team relevant to the Eurocode assessment existing structure, has developed a document for the other subcommittee to develop the relevant part, the part relevant to existing structure. So it is desirable that other material, all material would be included. For example, in the Eurocode 2, plain bars will be included, and we hope that all material will be included in the other Eurocodes. I know that SC3, relevant to steel structure, is working on a part on existing structure.
Thank you very much for that, Fabrizio. And I recall, just in relation to that question, an excellent publication from a number of years ago, specifically on the issue to do with cast iron structures and upon methods to probabilistically characterize the performance of the materials. If I could remember the reference, I'd give it to you directly, but maybe I'll send it to Brenda subsequently, and she can post it. So the next question.
And
yes.
just Alan, it could be a good example for future work in this task group or in the future.
Absolutely.
Example.
Maybe this particular individual would like to join with the work of the task group going forward and bring that expertise on board. So the next question is from Ian Ferguson. And Maria, I'll give you this question because yours was quite an old structure. How is the condition of elements taken into account?
For FIB Bulletin 80 actually has condition that design value method can be used only if the structure is in good condition. And for our case study, visual inspection is provided with some simple non-destructive testing to be sure that the bridge is not under reinforcement, corrosion, and so on. So this presented method actually is available and possible only if the bridge is in good condition. If bridge is deteriorated, then this concept cannot be used. So I hope I answer this question.
Great, thank you, Maria. And I think very many of the people, for Ian, very many of the people on the webinar today have published papers over a number of years on very similar aspects to the question which you raise. So again, there's lots of literature, interesting literature out there which can be considered. Okay. And if you'd like to contact Andre subsequently, I'm sure he'd be happy to point you in the right direction. So the last question is a fantastic question to end on, I think, given the presentations which we've had today. And Andre, I'm going to give this one to you. What is the recommended beta for bridges? I saw 3.3 was used in the presentations.
Yeah, it's really, I think, the key question of the webinar today. I would say that there is currently a technical specification in Europe, the 17440, that opens the doors to reduce the beta value and leave the different countries to have some choice about this decrease. And it depends on some economic analysis and also safety analysis. So it is a key question in this study. We make some assumptions and we look at how the results would be changed if we reduce the target reliability level. And this is a question, I would say, maybe to be considered in different countries and to accept different levels. And here today, we are discussing about bridges, but the question is also concerning buildings. And there might be some differences considering the examples that we have to look at. I don't know if the other wants to add more about that. Maybe, I don't know, Fabrizio, you were in the committees of Eurocode, so maybe you have some opinion.
Yes, it will, in the Eurocode, it will be an NDP. So there will be differences from country to country, and this is an open question. In some previous draft, there was a general table for previous draft, also the technical specification you mentioned. There were some suggested values as for new structure, but following some discussion, the table was deleted, and now in the last draft of EN 1990, we have a table for new structure, and this can be used also in general for existing structure, but it's also written that modification are possible. So it is an open question.
Great, thank you both. I think that was a super...
Sorry, Alan. Yeah,
sorry.
Can I just jump in regarding?
Oh, Dominic, yes, absolutely. Sorry.
Regarding the beta question, yeah, it really is the key question, as Andreas said, because there is no anonymous answer, but JCSS recommends 3.3, if I'm not mistaken, depending on the consequent class and reference period. But I would like to point out some countries have their national codes where you have ways of calculating beta for bridges based on certain parameters, and there's also a really good paper by our colleagues from Slovakia. It's called Reliability Levels for Existing Bridges According to Eurocodes, which made they developed a research on calculating the beta regarding how old the bridge is and the remaining lifetime. So I would post a name of the paper here in the chat. So I would recommend everybody to take a look. They also used some methods which are similar to these, which we presented today.
Thank you for that, Dominic. Yes, go ahead.
Yeah, if I may. So today we present two aspects that enable to update the partial factor. There is, so as we say, the target reliability level, but there is also another key parameter, which is the uncertainty that we have on the variables. So if we have larger uncertainties, then it might also lead to increasing partial factors. And if we have, in general cases, some lower uncertainty on the variables, it could lead to have a lower value of the partial factors. So we presented some case studies today, but I think there is no way to generalize the results to families. It really depends on the case study we have when we try to have this updating, this adjusting of partial factors, and it depends on the context of the bridge. Yeah.
Thank you, Andre. Thank you all for that. And I think it would be remiss of me if I didn't point you to the work of our friend and colleague Dimitris Diamantidis, who has done a lot of work in this area over the years. I'm not sure if Dimitris is on the call today, but certainly if you refer to his publications over many years, you'll find some very interesting information. So I think that was a fantastic way to end our webinar today. I think that was a perfect question with which to conclude this webinar on the assessment of existing bridges with practical implication with case studies. I would like to thank all of our speakers today: Andre Orsesi, Fabrizio Palmisano, Vasul Boros, Marija Kuster-Maric, and Dominic Kukandic. I would like to thank you for participating today. I would point you to the e-learning webpage where a recording of this webinar and of all previous webinars is available. And really, I would encourage you, if you are interested, as you seem to be from the level of engagement we've had, I'm sure Andre will be very happy to receive contact from you all if you're interested in the work of the task group or next steps. So thank you all very much. I wish you a very nice weekend and thank you for your participation today. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.